Okay, today we're going to start talking about similar figures. So if you remember from Unit 4, which was our last unit, we talked about congruent figures. And congruent figures were figures that had the same shape and the same size, which meant that they had congruent angles and congruent sides. Well, similar polygons, it's a similar concept, except now the polygons have the same shape, but a different size. By the way, you're going to want to take some notes on this stuff, so feel free to pause the video whenever you need to. Jot down what you need and then continue on. So for similar figures to have the same shape, they're going to have corresponding angles that are congruent. And for similar figures to have a different size, they're going to have corresponding sides that are proportional. So let's take a look at this first example. It says trapezoid ABCD is similar to trapezoid PQRS. Before we move on with the question, I want to take a look at the statement that we're given. Just like congruency statements, we have similarity statements. And so we can say that trapezoid ABCD is similar to trapezoid PQRS. Now notice our symbol for similarity is different than congruence, so we lose the equal sign of the congruence and just have the tilde. The other important part about the congruency statement is that corresponding parts are in the same order. So if I want to know what angle B is congruent to or corresponds to, I look at the order. B is the second letter. And when I look at PQRS, Q is our corresponding angle there. So keep that in mind. That is very important to the similarity and understanding the orientation of the figures. So when we look at the question, what is the measure of angle R and the length of AD? Well, let's look at R in our congruence in our similarity statement. So R is here and corresponds then with angle C here. So we can see from our figure that angle C has a measure of 70 degrees because those are corresponding. We know in similar figures that angles are congruent, so the measure of angle R is also equal to 70 degrees. Now it asks, what's the length of side AD? Well, let's look at AD in our figure and notice that it's not labeled. So let's go ahead and give it an X because we're trying to figure out what that measure is and see what else we have in terms of sides. So we can see that AB has a length of 10 and maybe it has a corresponding side. So if AB is the first two letters in our similarity statement, then it corresponds to PQ. And PQ has a length of 6. Well, from that, we know that our proportion of our large figure to our small figure is 10 over 6. And we're going to use that ratio or that scale factor to set up a proportion to solve for x. So we look at AD. AD has a length of x. And AD, so we look at our similarity statement again, and see that AD corresponds to PS. Well, over here, PS is equal to 5. So we have a nice simple proportion. We can cross multiply and solve. We find that 5 times 10 is 50, and that's equal to 6 times x. Divide by 6 on both sides. 6 goes into 58 times with a remainder of 2 over 6. Or 8 1/3. So now we can say that AD is equal to 8 1/3. Okay, so let's take a look at this question. This one says, are these figures similar? If they are, write a similarity statement. So in order for figures to be similar, we have to go back and check. Are all of the pairs of angles congruent? And are all of the pairs of sides proportional? So let's look at our angles first. Well, we have this angle L, which is obviously congruent to angle Q. There's one pair. We have angle M, which is congruent to angle P, a second pair. And finally, are our third pair of angles N and R congruent? The answer is yes, because if you have two pairs of congruent angles, then your third pair are congruent as well, third angle's theorem. Okay, so all angles are congruent. That's the first check. The second thing is we need to check that sides are proportional. So we're going to look at this in kind of a systematic way. Let's start with the longest side of the biggest triangle. So that's going to be side MN, and it has a length of 20. 20 corresponds to the longest side on the on the smaller triangle, which is 8. So 20 over 8 is going to be equal to, then we're going to go with another pair of sides. So let's go with the medium length sides, 15 over 6. And finally, we're going to go with the shortest side, 10 over 4. We're not done there because we have to go ahead and simplify and see, is this the same ratio for each one of these pairs, or is it not? So 20 over 8, 4 goes into each of those, so that's going to be 5 over 2. 15 over 6, 3 goes into each of those for 5 over 2. And 10 over 4, 2 goes into each of those for 5 over 2. So we can see, because all of our sides have the same proportion or ratio, that the sides are proportional indeed. So yeah, the two figures are similar. And we can say that triangle LMN is similar to triangle when now we need to make sure that parts correspond. So L corresponds to Q, M corresponds to P, and that leaves N and R. Make sure that you have your work when you are doing this. Make sure that you are showing that all angles are congruent as well as sides being proportional. For this next example, I'm going to give you a minute to go ahead and try it, and then we'll go over it. Okay, if you're not done at this point, go ahead and pause the video, finish the example, and then pick back up where we're at, and we'll go over it. So here we go. We need to check for congruent angles first. So angle N is congruent to angle P. Good, one pair of congruent angles. Angle M is congruent to angle R, a second pair, which means that angle L and angle Q also have to be congruent. So now let's test our sides and see if they are proportional. So again, we're going to start with the longest side, 18, over the longest side of the smaller triangle, which is 12. With the medium sides, 12 over 9. And finally, the shortest sides, 10.5 over 4. Now, we know that we don't like having decimals in a ratio, so we're going to change that. We'll multiply both of those by 2 to 21 over 8. And we're going to reduce these and see if these are equal. So 3 goes into 12 and 9. That leaves us with 4 over 3. And 6 goes into 18 and 12, which leaves us with 3 over 2. So we can see that our sides, when everything is simplified, the sides are not proportional, so these triangles are not similar. Okay, so let's apply these rules and applications to real life. So you have a photo that's 4 inches wide by 6 inch long that you want to reduce proportionally to fit into a frame that is 1.5 inches wide. How long will the reduced photo be? Well, of course, we're going to start with a picture. And we're going to label our picture. We know that this is 4 inches by 6 inches. And we want to reduce this down into a frame that is going to hold a photo that's 1.5 inches by, we don't know, so we'll call it X inches. So let's set up a scale factor between our original photo and our reduced photo. So our scale factor is going to be 4 over 1.5. We've got corresponding sides there. And that's going to correspond to 6 inches, because we're going to start with the larger figure again on top, over X inches. And so from here, we're just going to cross multiply. If we're going to solve for X, 1.5 times 6 is 9, and that's equal to 4x. When we divide by 4, we get that x is equal to 2 and 1/4 inches, or 2.25 inches for the height of that photo. One of the things that we can take from similar polygons is not just a ratio of their sides, but also a ratio of their perimeters. So if you look at the theorem, it says if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding sides. So we know ratios of corresponding sides, like C over Z, is equal to A over X, and that's equal to B over Y. But what we can add to this is that the perimeter of our small triangle is A plus B plus C over the perimeter of our larger triangle, X plus Y plus Z. It's not a theorem that you necessarily have to know, because you can use the proportion of sides to solve for missing sides and then find the perimeter. But if you do know it, it can be a shortcut to some of the problems. So let's take a look at an example of one. You are constructing a rectangular play area. A playground is rectangular with length 25 meters and width 15 meters. So let's take a second and go ahead and draw our playground. It's 15 meters by 25 meters. And then let's take a look at our instructions for our play area. The new play area will be similar in shape, but only 10 meters in length. So that 10 meters is length, which corresponded with the 25 meters. And so we're going to take a look at the questions. It says, find the scale factor of the new play area to the playground. Well, this is our play area, our smaller one, and this is our playground, the larger one. So pay close attention to what it's asking for the scale factor. It says new play area to the playground. So play area to playground is 10 over 25, which reduces to 2 over 5. Or we can write it as 225. Part B asks us to find the perimeter of the playground and the play area. So if we know that our scale factor is 2 over 5, and we can find the perimeter of one of these areas, then we can find the perimeter of the other. So we use our scale factor, and we're going to set up a proportion. So the perimeter of our playground can be found because we have both dimensions. So we know that this perimeter is going to be 25 plus 15 plus 25 plus 15. So we end up with a total perimeter of 80 meters. Well, we can use that as our proportion and solve for the perimeter P of the play area. So we're going to cross multiply, and we'll get 5P is equal to 160. And when we divide by 5, P is equal to 32 meters. So the total area of the play area is 32 meters. Again, you could have just solved for this if you would have called this x meters and then found the perimeter afterwards. Okay, the last thing that we want to talk about is that if two polygons are similar, then you need to know that the ratio of any two corresponding lengths of the polygon is equal to the scale factor of the similar polygon. So that includes sides, widths, lengths, heights, altitudes, medians. They're all going to have the same scale factor. So if we know that this side over here is A and this side is X, obviously these two triangles, if they're similar, have a scale factor of A over X or X over A. If we know that its altitude has a scale factor of H, or I'm sorry, a length of H, and the altitude of the smaller triangle has a length of Y, then that scale factor of A over X is going to be the same as the scale factor of the altitudes, which will be H over Y. So again, that can be altitude, sides, medians, most likely any length that you can look at in a triangle. Some of those lengths we haven't talked about yet and will be coming in the next unit. That ends our notes for section 6.3, and now you have time to work on your assignment. Have a good day.